Hello again. These are two more problems from chapter 22. The first one is problem number 42 from the end of the chapter. The question is, what is the maximum torque on a 150 turn square loop of a wire that is 18 centimeter on each side, that carries a 50 ampere current and is immersed in a field of 1.6 Tesla. So I only draw one of these square loops over here. It doesn't really matter originally what the orientation is for the purpose of this problem, because we want to know what is the maximum torque. So here I draw the one loop. Each side L is 18 centimeter. The magnetic field, in this case, I just draw it outside the board. Again, it doesn't matter because this thing is going to turn around. The current I is 50 ampere. There are 150 turns, so N is 150. This magnetic field is 1.6 Tesla. So when is the maximum torque? What is the position, when compared to the magnetic field where the torque is maximum, meaning the force times the side is maximum? Well, we know that the torque is defined as the number of turn, the current A, B sine theta, where A is the area of the loop, B is the magnetic field, I is the current. Now the maximum torque is when theta is 90 degrees. So when sine theta is 1, this is maximum. And so plug in these numbers, you have 150 turns, 50 ampere, the area is 0.18 meters squared, that's 18 centimeter, so it becomes 0.18 meters square because it's a square, so that's the area. And then maximum torque is 389 Newton per meter. Be careful about the units here. This is a torque. The second question of this problem is, if you set the angle 10.9 degrees, what is the torque? Well, if the theta is 10.9 degrees, well then sine theta is not 1 anymore. And so you have 150 times 50 times 0.18 square times the sine of 10.9 degrees. If you plug in this number, you find that the torque is 73.5. The second problem is number 50 on the right over there. You have, it says the hot and neutral wires supplying DC power to a light rail commuter train carry 800 ampere, and they are separated by 75 centimeters. So something that you need to keep in mind here is that in this particular problem, and in case there are doubts, I will tell you, the two wires have current that goes in opposite direction. One is the hot and one is neutral. So one is going in one direction, one in the other. They're separated by distance R, which is 75 centimeter. And the first question is, what is the magnitude and direction of the force between 50 meters of these wires? So these are two wires carrying currents in two different directions. And so we know that the formula for the force between these two wires is the length of the wire, mu naught, which is the permittivity of free space. The current, in this case, the current is the same for both wires. So it will be I1 times I2, but because they're two the same, I do I square, divided 2 pi r, where r is the distance between the two wires. So when you plug in all these numbers, you get a force of 8.53 newtons. And this force is repulsive because they're going in opposite direction. Okay? Keep in mind that mu naught constant is 4 pi times 10 to the minus 7 Tesla meter over ampere. So make sure your units are consistent with each other. You know, we've been given 75 centimeters. We have to transform that in 0.75 meters. So everything all in the International System units, they're going to give you Newton at the end.